Welcome also from my side to everybody. I'm going to make a very, very small introduction to the tools that we have developed in EVENFLOW. This introduction just to give you a few things about the project, so you know what these tools became to be and how. Sorry. So this project is a typical RIA 3-something years project, 4 million funding, very focused. It ends in December. So that means what you're going to see today is the final versions of the tools, right? So the final outcome that comes out of that, of the project. Okay. So about the use cases, which is not the focus of today's webinar, but you should know where these tools were applied into. We had 3 use cases. One had to do with personalized medicine. It was about forecasting the tumor growth, especially taking into account the genes of the people, of the patients. And we looked for that for breast cancer, liver cancer, also health, head in the head, etc. The second use case was about infrastructure, and in particular, a water pipeline, right? So we had water pipelines where there were sensors deployed in them in regular intervals, and we used the signals from the sensors to be able to predict a leakage, or even detect it, if we don't manage to predict it. And where the location, of course, right? The third scenario was an Industry 4.0 scenario where we had a typical factory flow where multiple robots are working into that. And the problem was to try to avoid situations that like deadlocks and collisions, and to make every robot to reach their goals, avoiding bad situations. Okay. These were the 3 use cases, right, that we worked on. And the general approach we had and the tools we use for all these 3 use cases, besides the use case specific applications, were first a neurosymbolic pipeline, right? So we have perception data coming from sensors or whatever. Then with neural networks, we get some simple events out of them, and with neurosymbolic approach, we get some complex events out of that, which we can forecast, right? And that will be able to have proactive intelligence because we have the rules that for the neurosymbolic approach, which we know that have been enabled, which have been enabled, so that puts also some explainability into that, right? So for perception data to forecasting, this is the neurosymbolic pipeline. Complementary to that, we have the verification, let's say, tools, which they take the inputs and they make very careful sets of perturbations, and we try to verify our approach either for the predictions of the simple events or the complex events to verify that the models we have, they work as planned, right? If not, we need to retrain and go back again. And then the third line was the scalability challenges, where we have a large number of data, many channels, large velocities, large number of federated processors distributed across data centers. So we need we tackle this kind of problems as well, right? So they can have the first 2, let's say, processes running on them. Okay. So the tools you are going to see today are implementing the challenges of this that you see in this slide. The first tool is the Scalability Toolkit, which is led by Athena Research Centers, and Giatrakos will be the first speaker today doing this presentation. We have then the reasoning-based forecast interpreter, which will show the main neurosymbolic pipeline. This is led by NCSR Demokritos, and Nikos Katsouris will give the presentation. And then we have the verification tool, which will show how that works with the neurosymbolic pipeline. For approach, this is led by Imperial College London, and the speaker today will be Abdullah Hekal. Okay. There are many more things that we did in this project. For example, in the use cases, for example, when in the healthcare use case, we created synthetic data using variable autoencoders to measure the flow to create some flows, realistic flows of evolution of the tumors. Or in the pipeline use case, when we analyzed the number of sensors needed to be deployed and how much tolerance we have for failure. Or in the robotic use case with the Industry 4.0 use case, where we had a very nice simulator with supporting very realistically multiple robots and creating simulated videos, which fed a lot of training data. And many more activities in this project, but this webinar is about these tools, so I'm not going to take more time from you. I will just put these links here if you want to learn more, and you see on the screen, and I will give the floor to Nikos Giatrakos.
Thank you, Thanasis. I will share my screen. Can you please confirm that you can see my screen?
Yes.
Okay, thank you. So I'll use the laser pointer here. So welcome by my side. The first part of this series of presentations will be about the EVENFLOW Scalability Toolkit developed by Athena Research Center. As a short introduction, I would like to clarify upfront that scalability in EVENFLOW is based on two major pillars. First of all, parallelism. We distribute the computation among multiple workers or multiple devices, as we are going to explain. And data stream summarization. We have voluminous streams of data that arrive at high speed, and instead of processing all of them, we process representative summaries of the data. So as regards our scalability deadlines, we are going to give a presentation about the Synopsys data engine that we have developed and maintains stream summaries in parallel workers. Then we are going to introduce our Subito framework, which uses a novel Synopsys-based training paradigm that exploits the virtues of Synopsys in order to achieve a good balance between training accuracy in neural learning pipelines and training speed. This is also accompanied by parallel training across multiple workers and novel synchronization protocols. And of course, parallelism is also incorporated at inference pipeline. And we are going to proceed with presenting NeurofLinksep, a neurosymbolic complex event recognition engine that can operate on big data platforms and get the neurosymbolic computation distributed across multiple IoT devices. All these frameworks are integrated and implemented in state-of-the-art platforms, including Ray.io, Altair AI Studio, TensorFlow, PyTorch, and Apache Flink. Starting with our Synopsys data engine, as I said, in order to be able to process rapidly evolving streams of data in our training pipelines, instead of using the raw data, we use compact data summaries that preserve important properties of the raw streams, but allow us to process them efficiently in a short amount of time. So we have developed a Synopsys data engine on Apache Flink, which communicates with the outside world via Kafka, and it works as follows. Let's first concentrate on this red pipeline here, which receives requests initially for maintaining Synopsys. It parses them and then uses these register Synopsys and register request operators in order to design and assign the Synopsys maintenance burden into certain workers of a computer cluster. Now, these two operators do the same thing, but as we are going to explain shortly, they are used for different purposes. As new data arrive in the blue pipeline that you can see over here, they are parsed. the hash data operator consults from the register synopsis operator the workers at which this data item should be forwarded because they maintain relevant synopsis, and then it directs the tuple to those workers in order to update the maintained synopsis of the data. When we are talking about synopsis, we are talking about samples, sketches of the data, histograms, and so on, wavelets, and so on. Now, having maintained various synopses across a computer cluster this way, when a query arrives, it is parsed and visits the register request operator over here in order for the query to get directed to the workers that maintain a relevant synopsis. Now, the relevant synopsis may be maintained into one worker, in which case that worker directly delivers the output, or it may be partial synopsis may be maintained in multiple workers in a computer cluster, in which case we merge the partial synopsis and then provide the output. Lastly, when we have these instances of synopsis data engine across multiple clusters, we federate the partial synopsis, merge them, and then we provide the output. Now, this synopsis data engine is built on Apache Flink, which it's a powerful means of maintaining parallel synopsis rapidly. We also have developed versions of this synopsis data engine over Kafka streams, so that every synopsis is a microservice that can be deployed across IoT devices. But for learning purposes in particular, the integration of the synopsis data engine to Python pipelines was cumbersome. We had to convert the data into structures that are compatible with PyTorch and TensorFlow, with tensor compatible. Therefore, somehow the benefits of maintaining parallel synopsis were reduced. Therefore, we have a version of the synopsis data engine implemented on Apache on Dask, so that it is tensor compatible and can be used in Python ecosystems and learning libraries. Building on synopsis, we have introduced synopsis-based training optimization as a novel paradigm for rapid and simultaneously accurate neural learning pipelines. The Subito framework works as follows. Let's first concentrate on the blue pipeline over here. The blue pipeline ingests labeled streams of data from a Kafka topic and uses a learner. For now, we assume that this learner has a specific neural network architecture which trains for a specific epoch count and uses a specific synopsis and portion of the incoming streams. It updates the currently maintained neural model and writes its weights into this parameter topic over here. This parameter topic updates predictors in the prediction pipelines so that they can ingest unlabeled streams of data and provide predictions in the output as labeled streams. So we have a neural model that gets updated continuously and continuously gets deployed in the prediction pipeline for having fresh predictions on the unlabeled streams. Upon a concept drift, we have this module over here, which is an optimizer, and this optimizer, when a concept drift arises, decides how it should modify the neural network architecture, the synopsis size. Usually we use stratified sampling in this classification scenario, so the size of the synopsis, as well as the epoch counts that should be devised in order to change what this learner does, to change its model, its sample size from the input streams and the epoch count, to continuously balance accuracy versus training time. So this optimizer over here collects live input from the Kafka training topic and performs a number of trials using Bayesian optimization. In those trials, it attempts to learn the accuracy, the architecture, sample size, and epoch count that achieves the best accuracy versus training time balance using this formula over here. So after a number of Bayesian optimization rounds, we have a Gaussian process regressor that it can predict the combination of these three parameters that achieves the better accuracy versus training time balance and deploys a new model directly in the training pipeline. And the rest of the functionality explained previously continues unaffected. Now, the role of synopsis comes both at the optimizer side, because on par with the network architecture that we test, we vary the sample size that is ingested. So imagine that the neural architecture is behaving as an accordion based on how much data we ingest. It can be shallower or deeper to ensure real timeliness. And of course, in the training production pipeline, where the architecture and parameters devised by the optimizer are finally deployed. I will show you a demo of this, of the Subito framework. Now, in this demo, at the beginning, we also introduced the same concepts about the three software modules. Now, here you can see the training pipeline and the neural architecture that it is currently deployed, composed of various convolution networks and pool networks, as well as pool layers, as well as some dense layers. Now, as you can see, the setup is pretty laggy. We do not compress the data. We have the opportunity to train for only a couple of seconds of epochs, because the streams are unbounded, therefore we cannot keep them in memory for long. And you can see that the training time here, as a rolling average across various training rounds, is 35 seconds. Here you can see the prediction pipeline, where we essentially provide a histogram of each class that we see in the unlabeled streams that we ingest. And this is the area where optimizer suggestions are provided. If we forward the video a bit, but you can see that the entire interface is now laggy because the training process is too slow. Now we trigger the optimizer, which performs a number of training rounds in order to learn new accuracy versus training time trade-offs. And in the end, it devises the top 3 Pareto optimal-like solutions that it found. So you can see that we have the opportunity to compress the data a lot, training for a different number of epochs using these neural network architectures. And we also have some predictions about how the accuracy and the training time of the framework will evolve upon choosing one of these options here. So assume that we choose to deploy the option that lies in the middle, which means compressing the data by almost 90%, training for 5 epochs, and using a neural network with 2 convolutional, 2 pool layers, a flattened layer, and 3 dense layers. Now you can see that upon choosing this, the configuration passed to the training pipeline, and as we are going to experience shortly, after a while you will see the whole thing becoming much more interactive and also remaining actually ensuring good balance between accuracy and training time. You can see that the beginning accuracy and loss are unstabilized, but later on you see that we managed to reduce the training time to 2 seconds, and the whole interface gives the impression, and actually this is what happens, that it's much more interactive. Things are done in a real-time online fashion. Now, one step further, we have implemented everything using parallel learners. Each of these parallel learners maintains its own summaries, and we can further tune the parallelism degree that is to be devised in order to maintain parallel synopsis. These parallel workers operate under a parameter server paradigm, where we have incorporated novel synchronization protocols for further speeding up the training process, we have devised an EVENFLOW synchronization suite of protocols for achieving that. Also, the prediction pipeline is performed across a number of parallel predictors where we also incorporate an optimization involving batch predictions to further boost throughput. The last software module that we have developed is NeuroFlinksep, which conveys neurosymbolic complex event recognition and optimizes it across IoT platforms. NeuroFlinksep is composed of two major novelties. The NeuroFlinksep operator, which actually is used in order, first of all, to transform perceptual raw streams into symbols. This is done by encapsulating a previously trained neural network in a nested operator, which is called synapse flow operator. So this one ingests perceptual streams and converts them to symbols so that they can be used into Flinksep, which performs the complex event recognition process. Now, it is important to note here that the user does not need to write any program, but they should provide a regular expression accompanied by selection strategies and consumption policies, as well as windowing operators in order to define this NeuroFlinksep operator. And as we are going to see shortly, this NeuroFlinksep operator is incorporated in a state-of-the-art data science platform, namely Altair AI Studio. On top of that, we have the DAGstar for Share Optimizer, which upon receiving a workflow composed of many neurosymbolic operators, NeuroFlinksep operators, it performs assignment of operators to network devices across an IoT platform. So DAGstar for Share does not only choose devices on which NeuroFlinksep operator are executed, but also performs additional share-specific optimizations, including pattern decomposition, early filtering, reordering, and push of predicates upstream to reduce communication. This is the overall picture of the NeuroFlinksep architecture. The user provides a logical workflow which incorporates the application logic, but it is deprived of any physical execution details. This workflow has NeuroFlinksep operators besides traditional stream processing operators. This is done in a canvas provided by RapidMiner Studio by Altair. There's a workflow parser here, which receives the logical workflow that is drawn, finds the neural network that is appropriate for the application field, and gives the logical workflow to the DAGstar for Share Optimizer. The DAGstar for Share Optimizer searches among potential candidate physical execution plans. It chooses the optimal one and provides the physical plan to the job dispatcher, which is responsible for submitting Flinksep jobs, neural network enhanced Flinksep jobs that are assigned for execution in the various devices. A video that demonstrates the previous discussion. Now, what you see on the screen is RapidMiner Studio. This is a streaming optimization operator. The DAGstar for Share Optimizer is used, and in this streaming optimization operator, we provide interconnection so that the operators assigned to various devices can communicate via Kafka. There is a connection to the DAGstar for Share Optimization service, and we have a cloud side as well as 2 Raspberry Pi devices that are used. Now, if we double-click in this streaming optimization operator, we can draw the logical workflow, which includes 2 NeuroFlinksep operators. In this particular case, we are processing data for our robotic smart factory scenario within EVENFLOW. And in each of these operators, the user should provide a regular expression, a window size for applying windowing operations on the incoming streams and symbol, selection strategy, consumption policy, and also provide the path of the trained neural network to be used for perceptual to symbol data conversion. For instance, this operator is configured to detect a station skipping where a robot heads towards a production station in the smart factory, and then it misses the station directing to another one. And also we have another neuroflinks operator here. Now, if we press the submit button, Dagstar for sure we decide the placement of operators to devices, and besides the logical workflow, it gives a physical workflow. You see two parts. This part will be executed in a Raspberry Pi, while this part will be executed on the cloud side of the network. And if we double click in these operators, we can see that if I forward a bit, the part of the workflow that is assigned for execution on each device. And here we have the FlinkSep jobs that are registered and are currently running. Here you see the dashboard where robot movements are tracked across various stations in the smart factories, and also the events of interest are detected and pinpointed here. Now, the overall vision for a scalable neurosymbolic pipeline incorporates the three components we previously discussed. We have the synopsis data engine that provides synopsis to the Subito pipeline, which in turn keeps maintaining up-to-date neural models that can be deployed in neuroflinks operators to disseminate neurosymbolic computation across IoT settings. This is pretty much what we describe over here. That will be all by my side. Thank you for your attention. I will stop sharing, and I think Nikos Kajouris is coming next.
Thank you, Nico. And we'll give the floor to Nikos Kajouris. Just to remind you, if you have any questions, please keep them at the end, or there's a Q&A session after the end of all the presentations. You can also type them in the chat, and we'll pick them up during the Q&A. Thank you.
So, hi everyone. I am Nikos Kajouris. I will talk about neurosymbolic event recognition and forecasting. First of all, I want to deeply apologize because, unfortunately, for some reason that nobody has been able to figure out, I haven't been able to share my screen, and I don't have videos of the demos of the things that I was thinking about showing run. So, many apologies for this. I will just do the presentation and kind of try to describe the demos in the parts that were supposed to run live to explain to you what the tools that we have been developing is about. So this is joint work with these people that you see in the slide, and we are part of the complex event recognition group in NCSR. So next slide, please, Faye. I would like to start with a few things about what this is, what is complex event recognition and forecasting. Nikos already referred to that, but let me take a moment to explain what it is. The way that we see it is that we have an event recognition system, an engine that takes as input these complex event patterns. These are typically patterns of symbolic nature, and it tries to detect combinations of simple events which are extracted from streaming input in order to detect complex events of interest in the output. So simple events are timestamp pieces of information, and complex events are spatiotemporal combinations of these simple events. As you will see, these patterns are of temporal nature. We focus on symbolic automata. And the point of forecasting, as opposed to recognition, is to reason about future event pattern completion. And there are several ways we do that in the project. We use probabilistic models with tools that we have developed prior to the initiation of EVENFLOW, but they're still very useful. And we have been developing forward recognition techniques, meaning using a generative model to make predictions about simple events, and then run your complex event pipeline, your neurosymbolic complex event pipeline, as if performing recognition on these streams to get the forecasts. So next slide, please, Faye. I think that we can skip this to save time. It is just a number of applications that we have worked on, but let's focus on a concrete one to give some examples. So next slide, please. So I'm using this example from human activity recognition from video. On the top left of the slide, we can see the perceptual stream. It's a video of images of people performing various activities in some area. And these streams, these sequences, these videos are passed through a neural network, which is used to predict some so-called simple events, which are, in our case, are low-level behaviors about the activities that people are performing over time. So, for example, person 1 is active at time point 12, person 2 is inactive, and stuff like that. And then we pass these predictions through the complex event patterns, which in our case are symbolic automata. So we all know what automata is, this computation device from basic computer science. And symbolic automata means that instead of having simple alphabets guarding the transitions, here we have logical rules. So for example, we have guard G1.3, which says that we move from state 1 to state 3 if a number of conditions occur. Like, for example, person 1 is active, person 2 is inactive, and the two people are close. In this simple case that I will use in the presentation, this simple example, each state in the automaton corresponds to one of the complex events that we want to predict. So state 0 is no event, state 3 is meeting, two people meeting together and interacting, and state 2 is two people moving together. So it must be, and we pass the predicted simple events to the automaton, and we detect the complex events. So it must be clear before we go into the neurosymbolic case that in this case, this could be seen as a loosely coupled neurosymbolic framework. So we have the neural part on one side, our neural network, and we have our logic on the other side. And all we do is just we pipe the output of the network into the logic. Next slide, please. What is neurosymbolic AI, on the other hand, is that trying to combine stuff from learning and reasoning, neurosymbolic and statistical learning, with logical and probabilistic reasoning to tightly couple these two components, the neural and the symbolic, in order to get the best of two worlds, if possible, right? So make sense of perceptual level data with with the neural learning, and then use symbolic reasoning for interpretability, correctness, robustness, and better generalization. Next slide, please. So why do we want to use neurosymbolic SERP to get event recognition, to get all these assets, all these advantages into the event recognition domain? So the slide shows how things are in the loosely coupled case. We need these classifiers, these neural classifiers, to make sense of the perceptual input of the images. But in the loosely coupled setting, these classifiers are trained in isolation. So we give some simple event labels to the classifiers, we train them to detect the simple events, and then we just pass the output to the engine to detect the complex events to the logic. This is suboptimal because the downstream task is ignored. And also, it's not always feasible because it requires a lot of labeled latent concepts of simple event data. But usually in practice, all that we have available is scarce complex event supervision. Next slide, please. So the other option is to use purely neural event recognition, where we have, for example, we can have some recurrent architecture or a transformer-based architecture that can deal with temporal data and just train the network with complex event labels to detect what we wanted to detect. But this has famous downsides, which are shown in the slide. So it's black box, no knowledge, it's brittle, poor generalization, and all these things. Next slide. And this is how Eurosymbolic event recognition looks like. We don't train with simple event labels anymore. We train with in an indirect fashion with only complex event labels. So And because of that, because of the differentiable inference that we are using, we are able to backpropagate, to compute a loss directly on the symbolic model, which is a differentiable module in this case, and backpropagate the gradients back to the neural model. And we can do that for label efficiency and also in order to enforce constraints in the neural network training. Next slide. The advantages are the exact opposite of the disadvantages of purely neural. And next slide. So what I want to talk about is the two tools that we have been developing in EVENFLOW. The first one is about neurosymbolic training, inference, and explainability. And the second one is how do we learn these complex event patterns in a neurosymbolic fashion, because we don't always know them and we want to extract them from data. So I will begin with the first one. Next slide. And next slide. And the first question is, how do we make this differentiable, this inference process differentiable? And this inference process has two parts. We have logical inference with the logic, with the guards that, as you recall, guard the transitions in our automaton in patterns. And then we have temporal inference, which means that we need to propagate this logical inference through time, through the automaton in order to get the results. And the first tool is called NESEA. It stands for Neurosymbolic Automata and does exactly that. Next slide. It works as follows. So in order to train it, we have these videos, sequences of frames, of video frames, which are labeled as positive and negative examples. So a positive example is something where the event that we're interested in learning occurs, and a negative example is something where it doesn't occur. And we have our knowledge. In this case, our knowledge is given, which we compile into a probabilistic circuit. A probabilistic circuit is a concise representation of our logic, which allows to perform probabilistic reasoning, do all the computations that are required for probabilistic reasoning fully algebraically and very efficiently. And so its advantage is that it allows to answer very hard probabilistic queries in linear time in the size of the circuit. So this compilation is called this knowledge compilation process allows to convert the logic into a circuit. And then we pass the input to the network. The network makes the simple event predictions, and the simple event predictions are also given to the circuit, which then is used to extract the guard probabilities. So as you can see, the automaton on the right-hand side of the slide is just a Markov chain. There are no guards anymore. They're just probability distributions over the outgoing transitions from each state, right? And this can be represented as a transition matrix. And then we can do, next slide, please. We can process the whole sequence. We can derive the distribution over the probability distribution over the states of the automaton at each point in time with simple matrix multiplications, which are also fully differentiable. So we have logical inference made differentiable via knowledge compilation and temporal inference made fully differentiable via converting into matrix multiplications. And so what we do is that we process the whole sequence, we arrive at the end, our prediction is the final acceptance probability, we take a loss, and then we backpropagate the gradients of this loss into our networks in order to progressively train the neural network to detect simple events, so as these simple events, these detections, these predictions, to be aligned with the logic, so that the neural network and the logic, they work good together. So that's the whole idea. We're not training, recall that we're not training here with direct labels, with simple event labels, only with the downstream labels. Next slide. Yeah, this is the first, no, go to the next slide. Okay, there's no need to show this. So the first demo was to show NESEA running in action on this simple application. It's not something special. It's just imagine a loss, the training loss being reduced, and the test F1 score getting increased, improved over time on this application about human activity recognition. The important thing to note, to keep in mind, is these results, these cumulative results over here, where the NESIA is compared with purely neural baselines. So we have a stack of a CNN and an LSTM. The CNN detects the images, and the LSTM does the temporal processing. And the other is CNN, which has a transformer instead of LSTM. And the important thing to note is the test set accuracies of these systems. And as you can see, NESIA beats its purely neural baselines, the purely neural baselines in all different learning rate configurations. A learning rate was used here because there wasn't enough. There was an exercise in a data small domain, not enough data, so not enough data to have a validation set. So in order to get the results, you need to fluctuate the learning rate. Why is that? Because the train and the test split are devised in a way that the test data are out of distribution. And what this means is that we train on entirely different videos from the ones that we test, right? So that the conditions in the video are entirely different, are significantly different, and this is reflected into the results. So why does NESIA perform better? Because the logic that it uses, which the user provides, we know that this logic is good for the particular application. This logic allows to generalize across these out of distribution settings and keep important features instead of overfitting to irrelevant features that we see on the training set as the neural baselines do. Next slide, please. So this is the bad part, the fact that I'm not able to show this. Once we train that, so we train it in any way we like. We can use downstream. We can use simple event labels if we want to make learning converge faster, to combat reasoning shortcuts and various other stuff. But in any case, we at the end of the training, we have a hybrid system. We have a neural network that has been aligned with the logic, and then it can be used together. So what this demo shows is that we select a sequence of frames where something interesting happens. And its purpose is to showcase that this whole thing, despite being a neural-based system, it's entirely open box. So it's entirely explainable. So you can monitor how the probability distribution over the states and the class predictions fluctuates over time, changes over time, how the simple event predictions, the probabilities of the simple events change over time, and how these things are affected by the actual rules, by the probabilities of the rules that we're using in our knowledge base, the automaton guards, and how temporal reasoning is propagating through time, through the automaton. An important thing that I need that it would be good to note here is that especially regarding explainability, and especially thanks to the formal probabilistic semantics that NESIA possesses, we are able to have tools that are valuable for explainability, like, for example, most probable explanations. Most probable explanations means that we're given a sequence, we're given a video, and we have a condition at the end. We want to compute some conditional probabilities. The condition is that this video, at the end of this video, for example, our logic, our automaton is in an accepting state. And the most probable explanation is guess the most probable state of affairs through time, up to that time, so that our condition is satisfied. So what is the most likely thing that could have happened regarding the simple events so that the recognized complex events or the forecast complex events are such and such? This is a very expensive query. It's NP hard in general, and systems that don't have a formal probabilistic semantics that try to replicate it just use crude approximations that are not faithful to what the system is actually doing. But this query we can have for free in NESIA, especially because thanks to the formal probabilistic semantics. As you can understand, this query is especially related to counterfactual explanations, right? So we generate things that answer stuff like what are the possible conditions if I change this factor over here? How would the world change in no likelihood? What's the most probable state of affairs if I change things? So we can do this counterfactual reasoning and understand what's going on in our application using this type of queries. Next slide, please. Okay, next I want to talk about structured learning. What this means is that with the things that we've been discussing so far, we assume that the knowledge, the complex event patterns are given by domain experts, but this is not always the case. And actually, more often than not, this is not the case. So we have been developing in the project techniques that allow us to learn this symbolic structure from raw data. So this joint neurosymbolic training, what this means is the task is the following. We need to learn an unknown symbolic model, a symbolic automaton from this raw data, and we also at the same time don't know how to map raw input to symbols. So our automaton is going to use these symbols, but these symbols need to be predicted through a neural network from the perceptual input. So we don't have a trained neural network, and we want to do this jointly. We want to progressively learn the patterns, the complex event patterns, while at the same time using the good bits of the signal, of the training signal that these patterns provide as a feedback in order to train the neural network. So these are the two main tools that we have in the project. The first is NESEA and the second is ASAL. ASAL, the basic version of ASAL is a purely symbolic automaton inducer. It can generate, it can learn symbolic automata from symbolic data at this point. And how the combination of the two works in a neurosymbolic setting is that our neural network over here passes distributions of symbols to NESEA and weighted noisy symbolic sequences to ASAL. What this means? It means that we get, instead of passing a probability distribution, we just pass the argmax prediction per point in a sequence, but the whole sequence gets weighted by an average entropy. So sequences where the predictions are, the network are uncertain for the predictions get down-weighted, and sequences where the network is certain get a high weight. And then what ASAL can do is that it can combine these weights in order to find the optimal solution, the optimal symbolic automaton, which satisfies the good data, the high weight data as much as possible, while discarding the bad data as much as possible. So this is the way to get into the neural regime with purely symbolic tools like ASAL. And then what we do is this thing over here, NESI generates a loss in the same way that we discussed previously. And we use active learning techniques in order to get the most informative query points. What this means is that we need to have a few extra simple event labels. We cannot just train this network with downstream labels only because we don't know any of these things. So we need to use active learning to get some of these labels. Next slide. No, there's a slide missing here. Can you go back a little bit? So we have, previous slide, please. So we have been experimenting with several active learning techniques over here, basic expected error reduction, variance versus certainty of the sequences, stuff like that. And we have promising results that show that actually we can train the two together. Next slide, please. But the problem with ASAL is that it's based on combinatorial optimization. As I said, it can be ported into a sub-symbolic regime via weighting the outputs of neural network. But the problem is, and its advantage is that given enough resources, memory and time, it will generate the best results that we can get. But the point is that how much is enough? So I'm showing over here that the memory in a data intensive a knowledge-intensive task is almost exhausted. So on my laptop, this is from my laptop. So basically, ASAL, it can be impractical quite often. It doesn't scale well, and it can be unusable on several occasions. So we have been developing a differentiable version of ASAL. Can you please move to the next slide? Where we use pure gradient descent to learn the structure, and we restrict the use of ASP, of answer set solving, of the solver. So ASAL is based on answer set programming, which is a method to do combinatorial optimization through logic programming. So we restrict the use of symbolic solving to post-processing, simplifying, correcting, revising the structure that is extracted from the neural network, which might be incorrect. And we do all the work for learning the structure in a purely differentiable structure, a purely differentiable way. What's the way to do that is by combining fuzzy and OR gates of various types to learn the automaton guards. So the automaton guards are represented as neural DNFs. That stands for disjunctive normal form, a way to represent Boolean formulas. And then the structure of the automaton is based on the same technique that NSEA uses, this dynamic programming stuff for propagating inferences through time. So I had a demo for that. So I have a run that shows it running for a few epochs, converging, and how to extract the rules. Rule extraction is based on thresholding, of course. We use L1 or L0 regularization to push most weights to zero, weights of the predicates that are used in the guards' bodies, and weights of whole guards, of whole rules that get discarded. And so you just extract, you synthesize rules by combining predicates with the surviving weights. And I think that's all. Next slide. Yeah. So I will summarize. NSEA is a probabilistic, logical, and temporal reasoning system that uses knowledge compilation in order to do end-to-end neurosymbolic training in a fully differentiable and efficient fashion, and it's also fully explainable. The resulting system, ASAL, is a system that allows for joint neurosymbolic training, can be combined with NSEA. It can learn from purely symbolic input, noisy input, or from some sub-symbolic input. And it has a fully differentiable version, which is much more scalable than the combinatorial optimization based one. So both these tools can be found, and users can play with these things at these GitHub repos. There are some examples from baseline and neurosymbolic domains, but also even more complex ones. So, and README instructions that users can use to play around with these tools. So thank you very much. And again, apologies for not being able to share.
Thank you, Nikos. Then we pass on to the last presentation of the day. It's by colleagues from Imperial, Abdel and Sherwin. You have the floor.
Yeah. Share my screen. Okay, hopefully you can see my presentation.
Yes.
Okay, so this tool is for robustness verification. I'm going to give a brief overview of what we mean by robustness verification in this context, and then I'm going to pass it over to Sherwin so he can show you the tool and the workings. So this is just going to be a general introduction to neural network verification, and then we'll move on to the actual use case that we have. Okay. So just kind of to take a step back, the full overview is that neural networks in general, they've been shown to be susceptible to adversarial perturbations. And by this, we mean that if you, for example, for a simple classification task, if you have a stoplight and you have kind of very limited constrained noise, such that the output image looks exactly the same to us, the neural network can misidentify this. So it can change its prediction from a stoplight to a speed limit sign. And obviously in a safety critical application, if you have kind of a robot moving or a car moving, an autonomous car moving, and it does this misclassification, it is quite bad. So what do we kind of define this in a more mathematical sense is that if you have a neural network and if you bound all possible perturbations around this, so for kind of a given input, you create some sort of bounding box. So for any perturbation around this input, we want to guarantee that it's safe, that it will always kind of give the same correct response, even if the input is perturbed slightly. And this slightly is defined by this value epsilon that we have here. So how this looks like in kind of a real system, you have some sort of input video, a robot moving with its camera. And there can be an infinite set of perturbations that can kind of occur. So white noise addition to the sensors, or even contrast change, a brightness change, a hue change, a mask color change, or grayscale, or even geometric changes. Okay, so what we want to do is to verify the robustness against kind of these different changes. So there's a verification tool that takes in this kind of classification network and tries to formally verify that for all these different perturbations or all 40 perturbations around this certain input, we're actually robust, or we are not robust, right? So if we're not robust, then no, we want to robustify our system. We want to make sure that kind of all our things are robust. Okay, so let me kind of pass this on to Sherwin now so we can go through the tool itself. Sure, please go ahead, and I'll stop sharing.
Thanks, Abdul. I'll quickly share my screen. Just a moment. Just a second, I'm just bringing my slides up. Okay. Sorry about that. So continuing from where Abdul had left us with, we are right now for the EVENFLOW project, we have developed a verification tool, and the use case that we are targeting is the industrial robot navigation use case. And for this, we have a convolution-based network, and that's a neurosymbolic system. As Nikos had mentioned, the system takes in inputs as a video which is like a set of frames as the input, and then it's passed on to several convolution layers. And here is the rough architecture of the system that we are going to verify. And the verification tool would give us robustness guarantees for different noises. And in our use case, we are focusing on white noise. So that's within the LP norm perturbation. And we would be providing robustness guarantees within certain epsilon ranges of how robust the model is within accuracy percentage. So it's a CNN network in our use case, which detects if two robot trajectories are colliding or not. And we use the DFKI robot dataset. And since we have limited data set that we have collated, we use cross-validation in order to improve the model accuracy. So these are the verification results that we see across different splits. As you can see, the epsilon corresponds to the amount of noise, input noise that we are adding in order to make the example an adversarial example. So we try to add epsilon amount of noise and see how the accuracy drops. As you can see, as the noise increases, we see that the model accuracy drops all the way up to 0. And we do this across all 5 splits using a verification tool. And so the clean accuracy of the model without any noise is 75%, but as the noise increases, or as we try to certify against the noisy inputs, we see that it drops to 0. So this model is certifiable for up to 10 raised to minus 6 noise. And with this, let me move on to a quick demo. As you can see, so this is the robot image. So here, if you can notice, this is the camera of one robot trying to perceive another robot. And here we can see that across the frames, the robot is moving, and we want to see if the robot trajectories collide or not. And this is what the CNN receives as the input. So moving on to the demo, we have a small demo use case because of the amount of time that we have. So what we do here is initially we provide some configurations for our tool. We provide the network configurations and all the file paths that are needed initially, and then we load the trained network. So here is the trained network that we have, or the architecture of the network. It's a simple convolution network, and then followed by a classifier. So here we have 20 classes, and we are trying to find out the trajectories based on these classes. So after this, we try to load the saved network, the trained network, and then we are going to begin the verification process. So for that, the next step is to load the dataset. We load our dataset, and then let's take an example. So we just taking the first example of our dataset, and then we're trying to see how robust it is with a noise, say, for example, 1e raised to -1, which is highly noisy, and we expect it to be non-robust for it. So we add noise to this input, and then let's try to visualize how it looks like. So as Abdel mentioned, from a human perspective, this noise does not make any difference to the human eye, but for the model, it's not the same. So what we try to do here is we try to make use of the AutoLERPA library. See, the AutoLERPA library is an open source library that's has got various methods for verifying robustness of neural networks. In the underlying neurosymbolic model, the neural part is verified using the AutoLERPA library. And when we use the AutoLERPA library to compute the lower bounds and the upper bounds that we get, we are able to classify if the sample is robust or not. And as expected, we find that it's not robust for this noise. Although to the human eye, it does not make much of a difference. And let me also show you another example when we try to reduce the noise for the same input. We can see that it is the model is able to perform better. So we try to reduce the noise. In this case, it's 1e -7. And then we again try to add noise to this amount of noise to the same input. Now, when we visualize it, again, to the human eye, it doesn't make much of a difference because it looks, both the images from the original input and the noisy input looks the same. However, to the model, this time we are able to find that the sample is robust. So in this way, we iterate through the entire validation data set, and then we try to provide the worst case robustness guarantees for each input. And that is the results that we saw previously in the slides. So as the input noise increases, we generally expect the model robustness to go down. And we try to certify the model at a particular epsilon, the worst case robustness guarantees, or the worst case accuracy that it can get for white noise in this case. So that is the small demo that we had. And the toolkit is available in the EVENFLOW repository. It's called NESI Verify, and it's available publicly. So I would ask you all to check it out. So thank you so much.
Thank you, Sherwin. Abdel. We are now in the final Q&A session. So now it's time if you have any questions to ask them, or any of the speakers. I can see there is one question for the Subito tool in the chat. Maybe Nico Giatrakos,
Yes.
you can take that.
So yes, Thank you, Adonis, for asking that. We have two questions. One is what type of synopsis is used to achieve online training. Currently, what we employ, of course, the Synopsis data engine, as you know, since you developed it on Apache Flink. So the Synopsis data engine supports a wide variety of synopses. For now, we perform stratified sampling on each of the classes that are involved of the incoming streams. But to answer the second question, I would prefer to share my screen again. So the second question involves the adaptivity, how we can configure the size of the synopsis. As we mentioned, synopses play a role both at the optimizer side and at the training production pipeline. Now, as regards the optimizer uses the engine in order to test different neural network architectures and the different compression ratios and the different sample sizes. So here it performs a number of trials testing different compression ratios, obviously a value between 0 and 1, how much we compress the incoming streams. Now, it devises an neural architecture, a sampling rate, and an epoch count that is deployed in the training pipeline. After this point, to adapt the compression ratio, the rate at which we draw samples from the incoming stream, we need to find a concept drift. Currently, we monitor concept drifts based on a KL divergence measure. So the synopsis size is adaptive between consecutive optimization rounds, but without a concept drift, the sampling rate remains steady in the learning pipeline. I hope this answers your question. If not, we can reiterate on that. And another thing I did not note is that training here takes place in disjoint windows. So this is why you see this accuracy and loss plots are going up and down. It is not because the model never converges. It oscillates because we produce new models for every given window, and of course, windows are parameters that the user can tune so that they are more large or narrower. I hope this answers the questions. I will be happy to elaborate more.
Any other questions or any other speakers? There goes a lot of information being passed on. The tools, you can find more about the tools in our website. I think the link is in the chat already. And if you want to contact the speakers again, you can do it offline. They are available. So by mail or whatever. So if there are no further questions, maybe we can close. We would like to thank you all for attending. The presentations will be made public. I mean, the video of the presentations, this webinar will be made public. So you will be able, you can study it also at your own time. Thank you very much.